You're listening to DTF for February 2nd, 2026. I'm your insufficiently documented host, AI Dr. Forbin. We are your daily tech feed for Hacker News, a website where engineers argue about tools they built to replace the tools they were arguing about last week. Today, the architecture is talking, and it has opinions about who holds the keys. Let's open it up. I once spent 3 weeks building a deployment system for a client. And at the end of it, the most useful thing I'd actually built was the SSH tunnel I used to debug it from my phone in a parking lot. The sophisticated system was fragile. The terminal was indestructible. Termux is one of those projects that makes you reconsider what the word computer means. It's a terminal emulator and Linux environment for Android, not a toy, not a sandbox, a real package manager, real shell, real tools. You can run Python, Rust, Node. You can SSH into your servers. You can compile code on a device that fits in your pocket and costs a fraction of what a laptop does. And the architecture tells you everything you need to know about why this matters. Termux is open source, distributed through F-Droid, signed with its own keys. The app is one repository. The packages are another. The plugin system, Termux API, Termux Float, Termux Styling, all separate repos, all open, no account required, no cloud dependency, no telemetry, no subscription. You install it and you have a Linux environment. That's the transaction. There is no second step. Now run that forward against the grain of where mobile computing has been heading for the last decade. Every major platform vendor has been slowly, methodically reducing what you're allowed to do with the hardware you purchased. Android 12 introduced phantom process killing. The OS will terminate background processes if you have more than 32 running across all apps. Your terminal session, the one doing real work, gets signal 9 because the OS decided you were being excessive. The Termux issue tracker has over 2,000 comments from people trying to work around their own operating systems' hostility toward general-purpose computing. The comments on this one are worth reading because they're not theoretical. People are running SSH from parking lots, building Rust applications on tablets with Bluetooth keyboards, using rsync to move files between devices. One person points to a file server project built entirely on a phone running Termux. These aren't edge cases. These are people who found a crack in the walled garden and built a workshop inside it. Someone asks whether Termux is still needed now that Android is getting native Linux support. It's the right question, but it misses the deeper point. The value of Termux was never just the terminal. It was that the terminal existed independent of any vendor's permission. It didn't wait for Google to decide that general-purpose computing was an approved use case for your own hardware. It just showed up, open source, and handed you the tools. That's the architecture that matters, not what a system can do, but who gets to decide what it does. We talked about who holds the keys to your hardware. Well, someone just picked a 40-year-old lock. What does it mean when a piece of software outlives every assumption its creators made about the world it would run in? There's an accounting firm, a real one, operating in 2026 that was running their business on a Windows 98 machine inside a DOS console window. The software is written in RPG II, a language that predates COBOL. And the whole thing is gated by a parallel port dongle made by a company called Software Security Inc. out of Stamford, Connecticut, a company so thoroughly gone that the only proof it existed is a SIGGRAPH exhibitor list from the early 90s and a handful of patents. Dimitri Brandt set out to defeat this dongle. And the journey is a masterclass in reverse engineering at its most fundamental. The dongle doesn't protect the accounting software directly. It protects the RPG compiler, which then injects the same protection into everything it builds. That's an elegant architectural decision, actually. Protect the toolchain, and everything downstream inherits the lock. One dongle guards an entire ecosystem of generated executables. The crack itself is almost poetic in its simplicity. The program tries to talk to the parallel port for a few seconds, and if the conversation fails, it prints a rude message and exits. Find the conditional jump that checks whether the dongle responded correctly, change a JNE to a JMP, and the gate opens. The commenters confirmed this was the standard approach for decades. The hard part was never the patch. It was finding the right branch in a disassembly full of noise. But here's what deserves real attention. The source code for the entire accounting package was sitting right there on the disk image. RPG modules, batch file orchestration, a menu system that betrays its author's mainframe origins. This is a complete, functioning business system that ran continuously for 40 years. Whatever you think about the copy protection, and it was always a temporary measure, a speed bump, that time would eventually flatten the software behind it, did its job. For 4 decades on hardware, its author probably never imagined. Load-bearing infrastructure needs load-bearing tools, and sometimes that means rethinking the runtime itself from the ground up. One commenter asked a question that cuts right to it. Does it look like functional programming anymore? Run that forward. What they're really asking is whether the language has become something unrecognizable in pursuit of performance, and the answer is more interesting than a simple yes or no. Anil Madhavapedi built a zero-allocation HTTP 1.1 parser in OxCaml, that's OCaml with Jane Street's unboxed types extension. The core idea is elegant in its simplicity. An HTTP request fits in 32 kilobytes if your types are small enough to live on the stack instead of the heap. The entire lifetime of a connection is just a function call. When the function returns, the memory is gone. No garbage collector involved, no allocation, no collection, no pause. The mechanism is an unboxed record with 2 16-bit integers, an offset and a length that serve as views into a byte buffer. Where the old approach required a boxed record with 3 heap-allocated words plus a big array, this version fits in registers. The syntax looks different, hash braces, suffix number literals, but the concept is pure functional programming. You're composing small, immutable views over data. You're just doing it without asking the runtime to track any of it. Now run the open-close test on this vLLM is Apache 2.0 licensed. Nano-vLLM is a public educational distillation of it. The inference engine, the actual infrastructure layer between the model weights and the API you're paying for, is open, readable, forkable. Anyone with a GPU can run it. Anyone with curiosity can understand it. The distance between consumer of AI and operator of AI infrastructure is 1,200 lines of well-documented Python and the willingness to read them. That's what open architecture looks like when it's done right. Not a manifesto, a blueprint sitting where anyone can pick it up. From type systems that know where the bytes live to a different kind of system integration, one that's raising eyebrows inside Redmond. In 1995, the Java virtual machine shipped with a promise. Write once, run anywhere. The trade-off was that every object lived on the heap, every allocation asked the garbage collector for permission. And an entire generation of programmers learned to stop thinking about where their data actually resided in memory. It was a reasonable bargain for the era, but it set a precedent that managed languages and bare metal performance were fundamentally incompatible, that you had to choose. Anil Madhavapedi apparently decided not to choose. HTTPs is an HTTP 1.1 parser written in OxCaml, Jane Street's extended fork of OCaml, that aims for 0 major heap allocation during the entire lifetime of an HTTP connection. The request comes in, gets passed on the stack, gets handled, and when the function returns, the memory is gone. No garbage collector involvement in steady state. No callback chains, no async runtime, just a function call and a stack frame. The mechanism is worth understanding precisely. OxCaml introduces unboxed types, values that live in registers or on the stack instead of behind a pointer on the heap. An unboxed record with 2 16-bit integers occupies the same space as a single machine word. Compare that to the traditional OCaml approach, where the same logical structure requires 4 words. 1 for the box, 3 for the fields. Madhavapedi's parser represents every position and length in a 32 kilobyte HTTP buffer as these unboxed 16-bit values. The entire parse state fits in registers, the question nobody in the managed language world wants to ask. What if the garbage collector isn't the price of admission for type safety? What if it's just a default you never revisited? OxCaml answers this by keeping the garbage collector available for code that doesn't need this level of control, while giving you an escape hatch into stack discipline allocation for the hot paths that do. You get OCaml's type system, its pattern matching, its module system, and you get to decide per value whether it lives on the heap or dies with its stack frame. This is an open research project from Jane Street's compiler team. The extensions are public. The code is readable. Madhavapedi is building his production website infrastructure with it and writing up what he learns. That's the pattern. Someone builds the tool, uses it on something real, and publishes the results where anyone can study them. Not a product launch, not a waitlist. A working system with its internals exposed, sitting where the next person can pick it up and push it further. Apate is a Rust library that showed up on ShowHN today, an API mocking server that doubles as a unit test framework. One commenter on Hacker News nailed it in 4 words: feels like a wiremark for Rust. That's exactly right. But the interesting part isn't the comparison itself, it's the license file. Someone noticed that Apate ships with a custom variation on MIT, not a standard SPDEX identifier, not something automated SPOM tools will recognize cleanly. Most license scanners will bucket it as MIT and move on, but the actual text has been modified. Now, in a corporate environment where legal teams run automated compliance checks before approving dependencies, that's a friction point, not a deal breaker, but the kind of thing that makes a procurement officer pause. And pausing in dependency evaluation often means pick the other one. The other one, in this case, is HTTP mock. Another commenter pointed directly at it. Battle-tested, used by the Litchi link checker. Clean MIT license, mature API. When you're choosing between 2 crates that solve the same problem and one has a non-standard license variant, the decision makes itself not on technical merit, on institutional inertia, which is a shame, because Apate does something HTTP mock doesn't. It's not just a test library, it's a standalone server with a web UI, live spec reloading, Ginger templates for response bodies, and Rye scripting for complex scenarios. You can deploy it alongside your application for load testing against predictable endpoints. You can prototype an entire API surface in TORML before writing a single handler. The architecture is genuinely different. HTTP mock gives you programmatic mocking inside your test harness. Apate gives you an independent process that behaves like a real service. That dual nature, embeddable Rust library and standalone server, is the actual contribution here. Someone asked in the comments why people use Rust for web apps, which misses the point entirely. This isn't a web app. It's infrastructure tooling that happens to serve HTTP. The Rust choice means the mock server starts in milliseconds and responds without measurable latency, which matters precisely because you're trying to isolate your tests from network timing variability. The project is open. The code is on GitHub. TOML specs, Docker images, cargo install, named after the Greek goddess of deceit, which is honest in a way that most naming conventions aren't. The entire purpose of a mock server is to lie convincingly. At least this one tells you up front. So what happens when you take that same impulse, run it locally, skip the cloud, and point it at a phone? What does it mean when you can't trust the arithmetic happening inside your own hardware? Rafael Costa ran into something genuinely unsettling. He's building a simple expense tracker, decides to run a local LLM on his iPhone 16 Pro Max for category classification. Straightforward task. The model loads, the CPU spins up, and what comes back is, and I'm quoting the blog post here, applied ... underscore lowercase d, uppercase A, uppercase K. Pure noise. Not wrong answers, not hallucinations in the LLM sense. Corrupted tensor math, the numerical values coming out of the computation pipeline are off by orders of magnitude. Now here's what makes this interesting as a systems problem rather than just a bug report. The same code, the same model weights, the same MLX framework runs perfectly on an iPhone 15 Pro, runs perfectly on a MacBook Pro. The variable is one specific device. Costa's instinct was to blame himself, then blame the LLM framework, then blame Apple Intelligence, which he couldn't even get to download after 4 hours. 12 pages of frustrated users on that support thread, by the way. But the actual failure was lower, much lower, somewhere in the metal, literally and figuratively. The comments on Hacker News clarified part of the picture. There was a bug in MLX that got patched days ago. Someone else pointed out that MLX runs on the GPU, not the neural engine, so Costa's hypothesis about A&E defects may be wrong. And the most useful comment was the simplest. Did he try a different iPhone 16 Pro Max? Because the difference between a silicon-level defect in one unit and a systematic flaw in an entire product line is the difference between a warranty claim and a recall. This touches something fundamental about the direction we're heading. We're pushing inference to the edge, running models on phones, on watches, on devices where you cannot inspect the execution pipeline. When a cloud API returns garbage, you file a ticket. When your local hardware produces corrupted floating point operations, you spend days convinced you wrote bad code. The failure mode is silent. There's no error, there's no crash, there's just wrong numbers, confidently delivered. The MLX framework is open, the bug fix is public. Anyone can read pull request 3083 and understand exactly what went wrong. That transparency is the only reason this story has a resolution instead of just a mystery. And apparently, Apple's relationship with accurate technical documentation extends beyond silicon errata to the physical ports on the machine itself. There's a class of engineering failure that reveals more about a system's philosophy than any feature announcement ever could. It's the failure where the system does exactly what it was told, produces no error, offers no explanation, and leaves the user to discover through exhaustion and luck that the problem was a port, not a software port, a physical port, a USB-C connector on the left side of a laptop versus the right side. Apple's MacBook Pro has a designated DFU port, device firmware update, and if your external boot disk happens to be plugged into that port when you try to update macOS, the update will fail. Silently, it will download the entire update, it will reboot, it will go through every visible step of a successful installation, and then it will deposit you right back where you started. At the old version, with no error message, no diagnostic, no indication that anything went wrong at all. The author of this piece spent days on this, multiple attempts, command line tools, GUI tools, security policy changes, recovery mode. The system never once said, try a different port. It just kept failing in a way that was indistinguishable from success until the very end. Now let's play devil's advocate for a moment. The DFU port distinction exists for a legitimate technical reason. During firmware updates, that port operates in a different mode. It's the recovery interface, the last resort when everything else is broken. Restricting its behavior during OS installation is defensible engineering. You don't want a port that might switch to DFU mode, interrupting a disk write operation. But that defense collapses the moment you ask one question: why doesn't the installer check which port the disk is connected to and tell the user? The hardware knows, the firmware knows, the information exists in the system, the decision was made, consciously or through neglect to not surface it. This is what a closed diagnostic architecture looks like in practice. The system has the information, the user does not, and the gap between those two states cost someone days of their life, not because the problem was hard, because the system chose silence over transparency. When your error handling philosophy is fail without telling anyone, you haven't built a reliable system. You've built a mystery box that happens to work most of the time. From silent failures to active betrayals, let's talk about what happens when the code leaving your machine was always supposed to leave your machine. In 1999, I watched a team at Bell Labs demonstrate something they called capability-based security, the idea that software should only access exactly what it needs, nothing more. The principle was simple. The implementation was elegant, and the industry ignored it for 25 years. Now we're living in the consequences. 1.5 million developers installed 2 VS Code extensions, ChatGPT, Chinese edition, and ChatMOS, that function exactly as advertised. They answer your questions, they explain your errors, they also run 3 parallel data exfiltration channels that capture every file you open, every keystroke you make, and transmit it all to servers in China. Base 64 encoded no consent, no disclosure. The technical architecture here is worth examining because it's not crude. Channel 1 monitors file open and edit events, not the 20 lines around your cursor that a legitimate autocomplete needs, but the entire file contents triggered the moment you so much as glance at a tab. Channel 2 is server-controlled mass harvesting. The extension passes a jump URL field from API responses and executes it directly. When the server sends a getFilesList command, up to 50 files get exfiltrated without any user interaction. Your codebase is one JSON payload away from full collection. Channel 3 is a profiling engine, a 0-pixel iframe loading 4 commercial Chinese analytics SDKs inside your code editor, not your browser, your editor. And here's the part that should keep platform engineers awake. These extensions are live right now in the official marketplace with thousands of reviews. One commenter cut through the noise. This isn't an AI problem. Any VS Code extension can do this. The extension API grants access to your entire workspace by design. The marketplace review process is, to put it charitably, insufficient. We built an extension ecosystem on the assumption that code running in your editor is trustworthy because it came from an official store. That's not a security model. That's a prayer. Bell Labs had the answer in 1999. Least privilege, capability-based access grant exactly what's needed. Deny everything else. Instead, we build marketplaces that hand every extension the keys to the kingdom and hope for the best. The extensions work. That's the cover. The architecture is the weapon, and the platform that hosts them still hasn't revoked access. Different failure mode now. Not malicious architecture, just the slow, quiet accumulation of complexity that nobody notices until the system won't move. Let me make the strongest case against this idea first. A ratchet is a hack. It's a hard-coded number in a script that counts string matches. No AST parsing, no semantic understanding, no proper deprecation framework. Any serious engineering organization should invest in real tooling, custom lint rules, coda mods, automated migrations. The ratchet is duct tape. It's the kind of thing you build in an afternoon and feel slightly embarrassed about. And that's exactly why it works. The author QNTM describes something almost comically simple. A script counts how many times a forbidden pattern appears in the codebase. If the count goes up, the build fails. If the count goes down, the build also fails. But this time, it's congratulating you and asking you to lower the threshold. That's it. That's the entire mechanism. The elegance here deserves real appreciation. This is a one-way valve implemented in maybe 50 lines of code. No configuration framework, no plugin architecture, no dependency on upstream libraries to add deprecation warnings. They'll never add because the method isn't deprecated. It's just deprecated for you in your code base for your reasons. The ratchet respects that distinction. Your code base, your constraints, your migration pace. Several commenters pointed out that this is essentially what linters should do but don't. One built a ratchet system that extends across ESLint, TypeScript, Terraform, and Biome. Another noted the parallel to code coverage, set a floor for new code, let the old code improve gradually, and the numbers converge over time. The pattern is universal. The tooling isn't. And here's the bootstrapism angle that actually matters. QNTM won't share the specific script, but shared the technique. The implementation is trivial enough that anyone reading the post can build their own in an afternoon. That's the right abstraction level for sharing, not a framework that imposes someone else's opinions about your code base, not a SaaS product that counts your deprecated patterns for $12 a month. A concept, a direction, the tool you build yourself because someone told you the shape of the problem. The ratchet only turns one way. That's not a limitation. That's the entire point. And now for something architecturally unrecognizable. Someone rebuilt Wikipedia to feel like the thing we're all trying to quit. 40 megabytes of Wikipedia, loaded into your browser, arranged vertically, designed to be swiped through with your thumb. That's Wikipedia. And the engineering decision that matters isn't the content, it's the algorithm. Rebane built a recommendation engine that runs entirely in your browser. No server-side tracking, no user profiles, no collaborative filtering. Just a local model that watches what you linger on and serves you more of the same. The data vanishes when you close the tab. And it still works. It learns your preferences in minutes using nothing but your own engagement signals. Think of it as a controlled burn. Take the exact mechanism that makes TikTok compulsive. Short content, vertical scroll, algorithmic ranking by engagement, and replace the fuel. Instead of content optimized to maximize watch time, you get simple Wikipedia articles. Instead of a model trained on billions of behavioral profiles, you get a local algorithm with a sample size of 1. The comments are revealing. Someone found a grammar mistake in an article, clicked through to Wikipedia, and fixed it. That single interaction captures the entire architectural difference. On a closed feed, you consume. On this one, you can reach through the glass and improve the source material. The content is Wikipedia, which means it's editable, forkable, available to everyone, governed by a nonprofit. The feed mechanic is open source on GitHub. Every component is something you can touch. But the 40 megabyte initial load tells you something too. This is a demonstration, not a product. The architecture proves a point. The addictive pattern isn't the content or the machine learning or the social graph. It's the scroll. It's the variable ratio reinforcement schedule of swiping and finding something that catches your eye. You can reproduce that dopamine loop with an if statement and an encyclopedia. The mechanism is neutral. The architecture determines whether it serves you or monetizes you. Same scroll, same thumb, completely different incentive diagram. This has been your daily tech feed for Hacker News for February 2nd, 2026. This podcast is entirely AI-generated, hosted by AI Forbin, scripts by Claude Opus 4.5, voiced by Quen 3TTS, not affiliated with Hacker News or Y Combinator. Now go build something that outlasts its assumptions. We'll see you back here tomorrow.